Afternoon, ladies and gentlemen. Welcome to Physics 2 Lab Report 2. My name is Nicholas. Let's get through this. Alright, first up the introduction. Now, the point of this lab was to identify the charges that were on each piece of tape, except this time we're doing it better than last time using calculus. Now, this was done by observing when the repelling force is equal or overcame the force of gravity, which is when the system is in equilibrium. Except this time, instead of just taking 2-point charges, we're taking the charge and we're spreading it across over a line like an actual tape is. Now, last lab we got a distance of 0.0127 meters when the system was at equilibrium, and the charge was identified as 4.2 e-9 coulombs. In this lab, there was a different charge value depending on how many sections we divided the line up into. At n equals 10 sections, we got 6.36. At 100, we got 6.696, and at 1,000, we got 6.6733, all e to negative 9 coulombs. Now, in this, we're assuming that the system is the top tape and the surroundings is the bottom tape and the Earth, which causes the force of electricity and the gravitational force, respectively. Formulas. Main formula here, main principle really, is Newton's second law, which is the net force equals mass times acceleration. And when that's equal to 0, that's when the system is in equilibration. And so we can set the force of electricity equal to the force of gravity, the negative force of gravity, because they're opposite. The electric force is the charge times the electric field at that point. The force of gravity is the mass times the gravitational acceleration. And then to calculate the electric field, first of all, we take the total charge and we divide it up by the sections, and then we're going to integrate that by the amount it changes. We plug into this equation right here to get the electric field at that point, like from that specific point, and then we integrate it to add up all of the points together to get the total electric field. In this, we are assuming that air resistance is negligible, and we're treating both tapes as having the same charge. Now, in case you don't remember, this is the experiment in which you take a tape and you move it up closer till the red tape up here moves upwards, and that's when you stop, and you know that's the distance at which they're in equilibrium, as shown right here on the right. Here are some code results. This is when we had 10 sections, n equals 10. You can see it's small. It's overall equilibrium, but you can still see the dots, and then as you can see, as we get more and more sections at 100 and 1,000, it gets to the point where blue is tiny, red is tiny, and over here you can't even see blue, and red is so small that you can only see it due to the contrast of the green. So how do we get this? First of all, the initial code, the initial values we're plugging in. Up here we have the position vector that's set the distance between the two tapes, as well as the amount of ends that we're using, the amount of sections. We got some mathematical constants, and then down here we got the mass of the total tape. And then down here, we've got the different charges that we use to kind of guess and check when they're equal to each other. And we would, of course, comment them out depending on which one we were testing. Code calculations. So this is where all the calculations are done. First of all, we got to find the electric field from a single charge. That's what this is right here. That's how we get dE at d top, is by calculating it using the dq, the small charge. And then using that, we then make all of the green arrows. That's what this line is right here, basically. It sets that and then makes the green arrows. Down here, we take that and we charge it by the dq of that, and that gives us the electric field, the dE. And then finally right here, this is just simple process of an integral by adding them all up until there's no more to add up. And then that's how we get the total electric field. Now, questions and possible errors. Easy possible error. The only possible error really in this lab is incorrect code. All the other possible errors are mostly attributed to the previous lab and are thus not really applicable in this lab. As for the questions, now what this question right here is essentially asking is, what is the difference between the previous lab and this lab in terms of our data? And the difference is that we got around 6.93 less depending on how many ends we got, and we had 4.2 e to the negative 9th coulombs. And what this shows is that this lab is a lot more accurate, and there was probably something wrong with our previous lab to have this much of a difference. Now, why do these values differ? Now, the reason why they differ is because depending on the position of the electron, it will have a weaker or stronger effect than other ones around it. And so the more we take into account of those like small, minute differences in distance, the more accurate we get the total electric field when we add them all up. That's why integrating it is so important in this scenario. That's all. Thank you very much.